New pictures caught by the James Webb Space Telescope have shocked specialists. Contrary to the way we might interpret the universe, these pictures uncovered an upsetting reality. Our current comprehension isn't adequate to make sense of the universe in its beginning stages, where the Big Bang hypothesis reaches its limits. This forces us to consider new speculation about its starting point. The inquiry emerges concerning how the universe was shaped exhaustively and why this new revelation challenges even the most experienced stargazers. Find out with us more about the Big Bang and the progressive details of the discovery. Before we dive into the specifics, we should review briefly the concept of the Big Bang, which is frequently referenced to depict the creation of the universe. Contrary to popular belief and some reevaluations, the Big Bang was not a blast in a prior space. Rather, it was space itself that began roughly 13.8 billion years ago, alongside matter and time, from a singularity. To explain in simpler terms, in the field of physics and astronomy, a singularity is a term used to describe spots where gravity is so intense that the curvature of spacetime becomes infinite. Yet, how could we be so certain about this today? Following billions of years since the start of the universe, we observe that our cosmic home is framed as part of a key interaction. For specialists, this addresses a fundamental component of the universe since its very existence: its apparently perpetual expansion. However, it is pivotal to understand that the universe isn't expanding into a pre-existing space. Rather, the space itself is continually expanding in size. Assuming we follow traditional hypotheses, it is estimated that the first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age when the first luminous celestial objects clustered together to form mature galaxies. However, the speed at which these galaxies developed is still a complex puzzle. A significant clue to solving this cosmic conundrum arose through the first pictures captured by the James Webb Space Telescope in July 2022. Specialists announced that the telescope had identified various galaxies, some of which had already existed about 300 million years after the formation of the universe. However, compared to the cosmic structures that formed in the millions of years after, these early galaxies appeared considerably smaller and less massive. This fits perfectly with the scientific model accepted by researchers. The density of matter in the young universe was simply not sufficient to lead to galaxies the size of those we observe today. What started as a discovery of 6 dazzling redshifted luminous spots separated from James Webb ended up triggering one of the major galactic mysteries of recent times. Now, although these newfound galaxies are similar in age to previous record-holding galaxies, they are nearly as massive as our own Milky Way galaxy. This has created an intriguing mystery in cosmic research. Thanks to a team from the Schmoor College of Technology in Melbourne, after examining a series of images captured by the near-infrared camera, the researchers identified the previously mentioned light sources. Using redshift, they determined that the light from these objects took over 13 billion years to reach our eyes on Earth. Thus, we are dealing with structures that had already existed between 500 and 700 million years after the so-called Big Bang. By examining the characteristics of these structures, it was concluded that the Webb telescope had captured 6 very early galaxies in the image. Surprisingly, these galaxies were so massive that they defied conventional cosmological expectations. Instead of finding the expected dwarf galaxies, structures were identified that were nearly as massive as our own Milky Way galaxy, despite having formed at an earlier age. If we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, and one of them might even have exceeded 10 billion solar masses. However, whether this possibility is valid is still not fully resolved. Even so, there would be significantly more stellar mass in the early universe than previously expected. The identified objects contradict nearly all traditional cosmological hypotheses. Even if only one of these galaxies turns out to be accurate, it would surpass the limits of our past assumptions to explain the presence of these structures. Furthermore, the density of matter in the early universe would have had to be multiple times greater than previously expected to account for this anomaly. Another equally puzzling explanation is based on the fact that these galaxies formed in a manner that is still entirely unknown to us. These discoveries and the debates surrounding the Big Bang are leading more researchers to question this hypothesis. Many cosmologists with alternative perspectives are frustrated that they are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as unwarranted mavericks. However, it is evident that even specialists who still defend the Big Bang hypothesis are constantly faced with questions without clear answers. These questions include specific issues such as why and how 13.8 billion years ago something literally emerged from nothing. Could something truly start from nothing? Or was there something triggering the event? Or was it all just a coincidence? Stephen Hawking pointed out that the concept of time as we know it began only with the Big Bang. Thus, this process could not have been triggered by something else or an external entity. A similar controversial question relates to the consistency of radiation and density throughout the universe. Regardless of which directions or distances we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Traditional researchers explain this hypothesis through the theory of cosmic expansion. However, other specialists take this assumption a step further with the theory of chaotic expansion. According to this idea, it is possible that this process has stopped only in certain regions, like bubbles, and continues indefinitely elsewhere. This suggests that multiple universes form in these bubbles, each with its own individual physical law. Considering this context, a key question arises: what if the universe does not represent the whole? More intriguingly, if another universe existed before our own, then the Big Bang would become an extraordinary cycle. In this hypothesis, concepts like start and end are ambiguous. What we typically refer to as the Big Bang might have been merely a transformation in a continuing process. When this universe exists, another one emerges from it. According to this viewpoint, our universe is part of a larger complex structure. Within this model, the idea of an external pattern of breakdown and resurrection of the universe is advanced. However, this is not the only perspective presented in the field of cosmology. Apart from the Big Bang hypothesis, in 1955, for example, an article appeared in NASA's Cosmic Times arguing that there might have never been a Big Bang, as the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the constant arrangement of matter could give the impression of a steady expansion of the universe. Another intriguing but controversial hypothesis comes from the universe of quantum physics and the simulation hypothesis. Some tests have proposed that our universe and everything in it might not actually exist. In simple terms, what we perceive as a universe could merely be a three-dimensional projection onto a surface. Hence, there is a possibility that our world is a result of a higher dimensional reality. While this may sound like the plot of a whimsical sci-fi film, it can be linked to the concept of a Type 3 civilization, which is capable of harnessing the energy of an entire universe and might create a perfect simulation. However, determining the reality in such a scenario is a highly complex matter. As researchers delve deeper into the mysteries of the universe, new theoretical frameworks are emerging that challenge our fundamental understanding of cosmology. One such theory is the multiverse hypothesis, which posits that our universe may be just one of many universes that exist in a larger, more complex multiverse. This idea extends beyond the chaotic expansion theory by suggesting that multiple universes could exist with varying physical laws and constants. Each universe within this multiverse might follow its own set of rules, leading to diverse and potentially vastly different cosmic phenomena. The string theory is another promising framework that seeks to address some of the limitations of the Big Bang model. String theory proposes that the fundamental constituents of the universe are not point-like particles but rather one-dimensional strings that vibrate at different frequencies. These vibrations give rise to the various particles and forces we observe. String theory has the potential to unify all fundamental forces and particles into a single theoretical framework, offering a more comprehensive understanding of the universe's origins and structure. However, the theory remains highly speculative and has yet to be empirically tested. The concept of cosmic inflation is also crucial in contemporary cosmological models. Cosmic inflation theory suggests that the universe underwent a rapid exponential expansion immediately after the Big Bang, smoothing out irregularities and setting the stage for the large-scale structure we observe today. This theory helps to explain the uniformity of the cosmic microwave background radiation and the distribution of galaxies. However, the exact mechanism driving inflation and the nature of the inflaton field, a hypothetical field responsible for this rapid expansion, remain subjects of intense research. Quantum gravity is another area of exploration that seeks to bridge the gap between quantum mechanics and general relativity. Theories of quantum gravity aim to describe the behavior of gravity at the quantum scale, where the effects of quantum fluctuations become significant. One such theory is loop quantum gravity, which suggests that spacetime itself is quantized and composed of discrete loops, rather than being a continuous fabric. This approach provides a potential explanation for the singularities predicted by general relativity and could offer insights into the earliest moments of the universe. Additionally, the study of dark matter and dark energy continues to be a major focus in cosmology. Dark matter, an invisible form of matter that does not interact with electromagnetic radiation, is thought to account for a significant portion of the universe's mass. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark energy, on the other hand, is hypothesized to be responsible for the observed acceleration of the universe's expansion. Together, dark matter and dark energy represent two of the greatest mysteries in modern astrophysics. The cosmic microwave background, CMB, radiation is a key observational tool in cosmology. It represents the remnant heat from the Big Bang and provides a snapshot of the universe when it was just 380,000 years old. Detailed measurements of the CMB, such as those from the Planck satellite, have provided crucial insights into the universe's age, composition, and the nature of its initial conditions. Anomalies or unexpected features in the CMB data could offer new clues about the universe's evolution and the validity of current theories. The anthropic principle is another intriguing philosophical concept that has implications for cosmology. It suggests that the observed values of physical constants and conditions in our universe are a result of the fact that they allow for the existence of observers like ourselves. In other words, the universe must have the properties it does because, if it were otherwise, we would not be here to observe it. This principle has led to debates about the fine-tuning of the universe and whether our universe is uniquely suited for life or merely one of many possible outcomes in a broader multiverse. Dark flow is a controversial and speculative phenomenon that some researchers have proposed based on observations of galaxy clusters moving in a direction that cannot be fully explained by the known distribution of matter in the universe. If confirmed, dark flow could suggest the influence of structures or phenomena beyond the observable universe, potentially providing evidence for interactions with other universes or regions of space. Hawking radiation, proposed by physicist Stephen Hawking, is another significant concept in the field of theoretical physics. This radiation is predicted to be emitted by black holes due to quantum effects near the event horizon. If black holes emit radiation, they could eventually evaporate over time. This concept challenges the traditional view of black holes as entirely black and non-emitting, and has implications for our understanding of information loss in black holes and the ultimate fate of these cosmic objects. The nature of time is another fundamental question in cosmology and physics. While the Big Bang model suggests that time began with the Big Bang, alternative theories propose different views on the origin and nature of time. Some theories suggest that time may be an emergent property rather than a fundamental aspect of reality, arising from more fundamental processes or structures. These ideas challenge our intuitive understanding of time and its relationship to space and matter. In the search for a unified theory of physics, the Grand Unified Theory (GUT) aims to unify the three fundamental forces of the standard model of particle physics: electromagnetic, weak, and strong interactions, into a single theoretical framework. While GUTs offer a more comprehensive understanding of fundamental forces, integrating gravity into this framework remains an ongoing challenge, leading to the pursuit of a theory of everything that would encompass all known forces and particles. The exploration of exoplanets and the search for extraterrestrial life have become increasingly important areas of research. Discovering Earth-like planets in the habitable zone of other stars could provide insights into the conditions necessary for life and the potential for life beyond our solar system. The study of exoplanets also has implications for understanding the distribution of planetary systems in the galaxy and the factors that influence planetary habitability. Neutrinos, elusive and nearly massless particles, play a crucial role in our understanding of particle physics and astrophysics. The study of neutrinos provides insights into fundamental processes such as nuclear fusion in stars and supernovae. Neutrino observatories and experiments aim to detect and study these particles, shedding light on their properties and their role in the universe's evolution. Finally, the philosophical implications of cosmological theories and discoveries continue to spark debate. Questions about the nature of reality, the limits of human knowledge, and our place in the cosmos are central to both scientific and philosophical inquiry. As our understanding of the universe evolves, it prompts us to reconsider fundamental concepts and explore new perspectives on the nature of existence. In summary, the quest to understand the universe is a dynamic and evolving field that encompasses a wide range of theories, observations, and philosophical considerations. As new data and ideas emerge, they challenge and refine our understanding of the cosmos, offering deeper insights into its origins, structure, and fundamental nature. Whether through the study of cosmic phenomena, theoretical frameworks, or philosophical inquiries, the pursuit of knowledge continues to drive the exploration of the universe and our place within it.